people at least working in algebraic groups. Secondly, I will talk about Albert algebras, what they are, how they are important, and their relations with algebraic groups. Then I go on to describe certain Galois cohomological invariants which are associated to these algebras with some properties they satisfy, which will be used up finally to give a solution of the problem up to what is called uh, moving to an isotope of the algebra. So this is roughly the plan. And I'm sorry, but I already apologize because I realized in the last minute I have goofed up in some places, but we will correct them as we go along. So let me just begin by defining what are central simple algebras over a field. So these are forms for the matrix algebra in the sense if K is a field and K bar denotes its some algebraic closure algebra over K bar. So the dimension of such algebras over K is therefore a square of an integer, uh, n square, then you call n the degree of D. So just a language here. For reasons, we know that every element in D satisfies a degree n polynomial. Perhaps that is the reason for the word degree here. We call D cyclic if you can find a subalgebra inside D, which is a field, and as an extension of K, it has dimension n. And it is cyclic, of course. So this is the notion of a cyclic algebra. So these are Galois algebras of a special kind. So you want the Galois group to be cyclic here. Then in 1920s, Wedderburn proved a very nice theorem for degree 3 central division algebras over a field that they always contain cubic cyclic field extensions of K as subalgebras. So this innocent looking theorem has many interesting consequences. So one can expect uh, such results to give rich dividends. And perhaps this motivated Albert to ask if every central division algebra, central division associative algebra over K of prime degree, that means dimension is a square of a prime, is cyclic. So if the degree is P, then the question was whether such algebras contain a degree P cyclic extensions as subalgebras. And this is in its full generality, it's still open. Of course, there are partial results, certain over certain fields, I think degree 5, one knows some answers. But in general, it's completely open. Please correct me, Philip, if I make a mistake. You are better expert on these things.
No, but what I know is that people's, I mean, do not think this is true, okay? So this
Oh, I
is the
see. That's
majority of colleagues do not believe, and
that's
Albert did not believe too, okay?
I
So,
see.
but 5 is a very special case. So for 5,
Yeah,
I don't.
it's very interesting that so many years have gone by, and only degree 3 is the satisfactory case, and 5 is still taking such a long time. But yeah, I don't know. It's interesting because it has. I saw your result on E8, so linking it with this problem for degree 5. So anyway, let's go on. So then Albert at that time was also working with these exceptional central simple Jordan division algebras, which we will not have to define this mouthful with so many adjectives. But these are algebras, what we will discuss today called Albert algebras. So the question was asked whether such division algebras contain cyclic cubic extensions of the base field. 5, and I wanted to say a little bit on what is already known. So in 1984, Petersson and Racine proved that if the base field contains cube roots of unity, then the answer is positive. So the Albert algebras contain uh, cubic cyclic extensions of the field. And in characteristic 3 case, this was done by Petersson in 1999. So in this talk, as I said, we will answer this question without any conditions on the characteristic or assuming anything on base field containing roots of unity and so on. But we have to shift to an isotope of the algebra. So I will define all these notions as we go along. Advertisement for this result. Recently, there have been two proofs of the Knesertitz conjecture for groups of type E8, certain rank 2 forms of E8 and certain rank 1 forms of E7. Both these algebraic groups have their anisotropic kernels coming from as certain algebraic group which one defines in terms of Albert division algebras. We will see that. So these proofs use this cyclicity result that I mentioned. So this is just a little advertisement for the result. So let me begin with now defining basic notions that we will play with. Albert algebra is. So here I will assume to simplify the exposition that characteristic is different from 2 and 3. This just simplifies matters a little bit. So let's fix an octonian algebra over K. I'm not defining this, what this is, but let's grant that for the moment. I'm sorry about assuming this here. Maybe there may be people who don't know this, but these are algebras obtained by, just like you obtain complex numbers from real numbers by taking two copies of real numbers, and then there is a product defined on them in a twisted fashion using the involution uh, and then you describe quaternion algebras by taking two copies of complex numbers, and then there is a product defined in them using the involution on the complex numbers. Similarly, octonians are obtained from quaternions by taking two copies of a quaternion algebra, and then there is a product defined there. So I will just leave this aside right now. So let's assume we know what an octonian means. So the property that I need for octonians, I will tell you later. So that's enough for us right now. So you fix such an algebra. So these are 8-dimensional algebras which are not associative, and they have a very nice quadratic form defined on them, which is multiplicative with respect to the algebra product. So as far as I am concerned, that should be enough for the moment. So let's fix such an octonian algebra over K and take a diagonal invertible matrix gamma over K, and let's define H3 of C gamma to be the set of all 3 by 3 matrices with entries coming from the octonian algebra C, which are Hermitian. So in the sense, so what is star here? So star is a certain involution. It's defined as, for any x in M3C, you define x star to be gamma inverse x bar transpose gamma, whereby x bar 1 means the 3 by 3 matrix obtained by putting bar on each entry. And this x goes to x bar is what is called the canonical involution on C. So there is an involution on octonian algebras, uh, and the norm of an element is that element times its conjugate. So this is the involution, and the algebra is defined here by looking at Hermitian matrices with respect to this involution. So this is as far as the vector space structure is concerned. We define a product there by symmetrizing the matrix product. So here you take x dot y to denote the usual matrix product of matrices x and y in M3C. So you symmetrize it, and this is a scaling factor here. So that is the definition of product in H3C gamma. So this product satisfies some properties. One is that the identity matrix is indeed identity element for this product of the algebra. And there is, because of this, you see that xy is yx for all xy. And then there is a weak associative law that these matrices satisfy. So these two conditions along with the identity element define what is called a Jordan algebra. So this is just for our purpose. I am not going into very general definitions, but these are called Jordan algebras. Algebras which are unital and are commutative and satisfy this weak associative law. This has degree 3 in the sense I defined before. Every element here satisfies a certain canonical cubic polynomial of this form, where TA is a linear form called the trace of the element, SA is a certain quadratic form, and NA is a cubic form. And these kind of algebras are called reduced Albert algebra in the literature. This nomenclature is very recent. Albert algebra was, of course, this nomenclature was given, I believe, in the 90s sometime, if I'm not wrong. This is the cubic form, and this has zero divisors. So this you will one is always able to find elements here which are non-zero, and n applied to them is zero. So this form has non-trivial zeros. There is this notion of the split Albert algebra. So instead of arbitrary C, we take C to be split octonian algebra. So this I talked about the norm quadratic form on the octonian algebra, and that is just defined as take an element x, take apply the canonical involution on C to x, call it x bar, then norm of x is x times x bar. That is a multiplicative quadratic form, what is called a Pfister form of dimension 8. And then one knows that such a quadratic form is either completely hyperbolic or anisotropic, meaning it has no non-trivial zeros. So if the form is hyperbolic, the corresponding octonian is called split. So we take the split octonian algebra and look at H3C gamma, then one can prove that in that case it is isomorphic to H3 of C with identity involution, identity matrix gamma 1, gamma 2, gamma 3, and that we denote by H3C. So this is what is called the split Albert algebra over K. So 3 by 3 matrices with entries in split octonian which are Hermitian with respect to the bar transpose involution. I am not going into the history of these objects. They were, of course, people in physics had hopes from these algebras, and that's why they were studied initially in laying foundations of quantum mechanics in some sense. And then, but they served more purpose in mathematics than physics at that time. Now, of course, things are mixing around, I guess. So let me now define what an Albert algebra in general means. So this will be an algebra over K, which when you base change to the algebraic closure of K, you get the split Albert algebra. So just like we defined central simple associative algebras, you can think of an Albert algebra in that light as those algebras which are twisted versions of the split Albert algebra. So I would like to stop here and ask if there are any questions. If people have any questions anytime, I will. These are Hermitian matrices, and over K bar they become the split Albert algebra. You can count the dimension of such algebras. That turns out to be 27. For the diagonal entries are living in the base field, so that is 3 dimensions, and above the diagonal there are 3 octonionic entries giving us 24. So that is 27. Below the diagonal are Hermitian mirror images of those entries anyway. So we get 27 dimension as the dimension of these algebras. And these support a cubic form. As I said, every element satisfies a degree 3 polynomial like this. Sometimes this is called Cayley-Hamilton polynomial for the algebra. Here Tx is a linear form, Sx is a quadratic form, and Nx is a cubic form. And we call that as the norm of norm of the Albert algebra A. So there is a dichotomy of these algebras. Either they are reduced, which means they have zero divisors, and which we can think of as non-trivial zeros of the norm form, or they are division algebras. So, either every element, non-zero element, has an inverse in some sense, or the norm form is isotropic. And this is detected by anisotropy of norm form. Division algebra, if and only if n is anisotropic, in the sense it has no non-trivial zeros over K. So this is as much as the notion of Albert algebra is concerned. I would like to describe two constructions of these algebras. These give all Albert algebras over a given field. These were known to Freudenthal as well, and then Tits also gave this independently, I believe. And both, sometimes people call them Freudenthal-Tits constructions. So how are these done? So you start with a degree 3 central simple algebra over K. So this is the minimal uh, requirement. We want to start with degree 3 central simple algebra, associative of course, and take a scalar from the base field, which is invertible scalar, and take 3 copies of D indexed by 0, 1, and 2. And let us denote the vector space direct sum of these three by JD mu. So there will be a multiplication mod 3 on this sort of some kind of mod 3 grading is here, Z mod 3 grading. On this, there is a product defined, and the product, when you concentrate on the zeroth component, looks like this. A00 times B00 is half of AB plus BA00. So I don't want to define the rest of the components, they're quite involved, but I want to tell you how the norm map looks like. Norm map looks like this. Norm of A, comma B, comma C, a typical element here, is the reduced norm of A plus mu times reduced norm of B plus mu inverse times reduced norm of C minus the reduced trace of ABC. So this beautiful cubic form is the norm form on this Albert algebra. These are what are called first constructions. And we mentioned Wedderburn's theorem, which said that every degree 3 central division algebra, associative central division algebra of degree 3 is cyclic. So using that, and the multiplication I told you looks like this on the zeroth component, that tells us that these first Tits construction Albert algebras are cyclic as long as I start with D, a division algebra. So I get a cyclic Albert algebra if D is a division algebra. And one knows for first construction that it is either split or it's always a division algebra. And its division one can detect by finding out if mu is norm from D or not. So this is a division if algebra if and only if mu is not a norm from D. So these are pretty classical results. Very useful result. We will come to this when we define the invariants for the algebra. And this construction I described is called a first Tits construction, and the parameterization is a central simple algebra D and a scalar mu. Together with these two parameters, we can define an Albert algebra structure on A, and the norm, as I said explicitly, looks like this. And I do need the norm, but not in very detailed way. As you will see, the proof of the result is pretty simple. There is another construction which is done by starting with a quadratic extension of the base field, and you take a degree 3 central simple algebra over the quadratic extension. So the center of this algebra is capital K, and sigma is an involution of second kind on B, In other words, it induces the non-trivial automorphism x goes to x bar on the center. So such involutions are called involutions of second kind. So you fix these this kind of algebra, and let's denote by B sigma plus the Jordan algebra of sigma symmetric elements. So you take those elements which are sigma symmetric or sigma Hermitian, whatever you like, and define the product of those two as half of x dot y plus y dot x, where x dot y is the product in B. So with this is a Jordan algebra in its own right of degree 3 again. And the next ingredients are take a pair of elements u comma mu, where u is an invertible element living in this algebra, and mu is a scalar from K, which is invertible. And the condition is reduced norm of u looks like mu mu bar. And such pairs always exist. There are plenty of such pairs. I'm suppressing a lot of details here. One can go on that, but let's just move on from here. So you pick such a pair. Once you have such a pair, you can immediately write down an Albert algebra on the vector space, which we will denote as J B sigma U mu. So these are the parameters. Each one is important here. If I take B and change the involution, the algebra changes. If I change U, the algebra again gives me a different Albert algebra and so on. So these are all the parameters defining the Albert algebra. And as a vector space, it is this 9-dimensional object. So these are sigma symmetric elements. So you can see that this is 9-dimensional over base field, and this is 18-dimensional over the base field. So the total is 27 dimensions. This has a Jordan algebra product which induces on the component, this component, the product xy that I defined here. So there is an algebra product here which I don't want to go into. I just want to mention the norm form of this construction. It looks like this. Norm of an element, typical element B living here and X living there looks like this. And one can, I'm afraid I may finish pretty quickly. This talk is going faster than I imagined. But perhaps people should ask questions if something is not clear. So this is a division algebra if and only if mu, this parameter, is not a norm from B. So this is the condition for division algebra. The moment mu is a norm, you get a reduced Albert algebra. Otherwise, it's a division algebra. This is what is called the second construction. And it is a form for the first construction in the sense when you base change to the center of B, you get the first construction. So if you proved these are Albert algebras, then this shows that this is also an Albert algebra and so on. So anyway, so these two constructions give you all possible Albert algebras living over a field K. So this much for these objects. I wanted to now digress to some algebraic groups that arise from these algebras. So that is really the interest to me. First, let's look at the split Albert algebra. So that, remember, were 3x3 Hermitian matrices with entries in the split octonian algebra. So if you take the split Albert algebra, which is unique up to isomorphism, and look at the group of all automorphisms of that split Albert algebra, then you get the split group of split simple group of type F4 defined over K. And therefore, coming from here, for any Albert algebra A over K, the automorphism group is defined over K and is simple of type F4. I'm brushing things under the carpet, but this is more or less straightforward. And what is more, all groups of type F4 arise this way. So the moment you start with a group of type F4, you can pin down using some representation theory, an Albert algebra whose automorphism group is that group. So these algebras are in their isomorphism classes are in bijection with groups which are simple of type F4 living over the base field. So this is as far as F4 is concerned. There is another important group associated to such algebras, what is called the structure group of the Albert algebra A. These are all elements of GLA, that means all invertible linear maps from A to A, which preserve the cubic form up to a scalar factor. So this is a fixed scalar, and this equation should be true for all x in A. So such elements form a subgroup of GLA called the structure group of A. Then one can prove that this is a connected reductive algebraic group defined over K of type E6. And this is the anisotropic kernel that I was talking about. So the group rank 2 form of E8 and rank 1 form of E7 I mentioned, there the anisotropic kernel has dimension 78, and that is the semi-simple part of this. The semi-simple part of this group is the group of all norm isometries. So you take nu f to be 1. So those f for which nu f is 1 gives you the semi-simple part of this group, the group of isometries. So that is the semi-simple group of type E6. Okay, so then there is yet another interesting group coming here. So you take any cubic étale subalgebra here. So there are plenty such. One can prove that easily. Pick one such and look at those automorphisms of the algebra which fix elements of L pointwise. So these are those automorphisms which fix all elements of L. L is fixed here. So one can show that this is a simply connected group of type D4 defined over K. I must stop here and ask if I am audible, because I'm sorry, my connection, internet connection conks out. So, okay, any questions so far?
Yes,
no
yes.
Yeah.
No. I have a question. Is that a trilitarian group?
Say it again.
This group OAL. Is it trilitarian with associated cubic?
I'm coming to that. I'm coming to your question. Yeah. Next page is exactly mentioning that. So as of now, this is a type D4. Just this is type D4. Let's go next to that. This is defined over K. Now recall that the Dynkin diagram D4 looks like a tripod, and the symmetries of this graph are S3, the permutation group of order 6. Now we can distinguish the type of this subgroup of automorphisms of A as according as the order of the image here is either 1, 2, 3 or 6. So you can show that this has type 1d4 if L is the split étale cubic, and type 2d4 if L is of this shape K cross delta, where delta is a quadratic extension of base field, and 3d4 in simple words the image is order 3 if L is a cyclic extension of K, and 6d4 if L is not a cyclic extension of K. And of course, depending on the arithmetic of the base field, in a reduced Albert algebra, all these cases can occur. But when we are in a division Albert algebra, obviously these will not occur because these have zero divisors. So these two are possibilities for division case, and both may occur. So we call, in this talk, we will call both of them as trilitarian types, just because they admit order 3 outer automorphisms. When A is an Albert division algebra, as I said, this group is trilitarian, and both these types uh, may occur. So there are examples where only this occurs. There are examples where, well, in next theorem will tell us that what is the importance of this. So this result says that cyclicity of an Albert division algebra is equivalent to asking whether the group of automorphisms has a k, a subgroup defined over k, which is of type 3d4. So one can prove here. So roughly, I'll just indicate how you prove such a theorem. So start with a subgroup of type 3d4. First of all, if you start with a subgroup like this where L is cyclic, then it is of type 3d4. That is quite okay. But the converse, if you start with a subgroup of type 3d4, then defined over k, of course, then you look at the fixed points of that algebraic group in the Albert algebra, and then you can prove that it's a cyclic cubic extension. So that is the indication here for a proof. Let me, if there are no questions, I will move to the next section, which is the definition of cohomological invariants associated to either the group of automorphisms or the Albert algebra itself. So let me introduce these invariants. So we know all the Albert algebras can be constructed using those two constructions I mentioned. So those are important to us in defining these invariants. One definition here, we call a field extension L of K a reducing field of an Albert algebra A over K if A tensor L is reduced. So very simple-minded definition. Then there is a theorem of Petersson and Racine saying that for any Albert algebra over K, there is a reduced Albert algebra H3C gamma defined over K, and this is unique up to isomorphism, such that for any reducing field L of A, when you reduce the algebra A going to that extension, you get an isomorphic copy of H3 C tensor L gamma. So this is extremely useful to us in defining invariants. This must have been in 90s sometime. Uh, so this H3C gamma that occurs here for a given Albert algebra is called the reduced model of A, since it is determined by A up to isomorphism. So to define invariants for A, we can make use of this reduced model as follows. So let's start with the reduced model of A, and NC denote the norm on C. So remember that is nothing but you take an element X in C and take the canonical involution applied to X and take the product. That is a scalar called the norm of X. This is a quadratic form of dimension 8 on C, and it is multiplicative. So though the algebra is non-associative, you can prove that NC of X times Y is NC of X times NC of Y. So that pins it down as a Pfister form of dimension 8. And I will say how it looks like. And gamma, as we remember, it's a diagonal matrix like this. We can scale this out and assume gamma 3 is 1, just not really important here. I'm just simplifying some expressions. Then there are two invariants one defines, which are invariants mod 2 for A. First is the F3 invariant, which is the class of this quadratic form living in H3. This is Galois cohomology. Notation here is, this is really, one should put the Galois group of the separable closure here, but one writes like this. So H3K is Z mod 2. And how does one get this? So this NC, one knows, looks like this. So this is the norm quadratic form of a quadratic extension of K. This is another quadratic extension norm. This is another quadratic extension norm. And one knows that NC looks like tensor product of these kind of three quadratic forms. So you can prove that you take any such expression and take the cup product of scalar classes where each scalar class lives in H1 K Z mod 2. So the cup product lands here. One can prove that this is independent of choice of expression for NC as tensor product of these kind of forms. So this is the F3 invariant living in H3 K Z mod 2. And F5 is defined by this formula. So for me, these formulae are not really important. What is important is some properties of these invariants that I will mention in a while. But point is this lives in H3 here, this lives in H5. So we will not need to remember much about these except that they live, this is a 32 dimensional form because you know this form is, so this is 2 times 2 4, 4 times 8, so this is 32 dimensional form. The invariant lives in H5. So any questions so far? And I hope I am audible. I have I I'm scared of my internet connection always. So the notation I used here is that this bracket notation I have used here, that is supposed to indicate a quadratic form which is diagonal quadratic form like this. And tensor product of two diagonal quadratic forms is the diagonal quadratic form AIBJ like this. So this is the notation I used. There is a theorem of Springer, which who proved that these two invariants, though not quite in this language of invariants, he proved that reduced Albert algebras are indeed determined by these two invariants. So if you have two reduced Albert algebras, H3 C1 gamma 1 and H3 C2 gamma 2, having the same F3 and F5 invariants, then one can prove they are isomorphic. So this is due to Springer. Then there is a mod 3 invariant that we need to define. So how does one define it? Remember, any algebra is either a first construction or a second construction. So first we define it for a first construction. First construction, the parameters are a central simple algebra D of degree 3 and a scalar mu, invertible scalar mu. So all we do is take the Brouwer class of D that lives in H2K mu 3. No, yeah, H2K mu 3. And then you take the scalar class mu in H1K mu 3. The cup product lands in the tensor product, lands in H3K mu 3 tensor mu 3, and that can be shown to be Z mod 3. So the cup product here lands in H3K Z mod 3. This is the G3 invariant of A. And when A is a second construction like this, you just go to the extension K. We know that the algebra becomes the first construction JB mu over capital K. There we define the invariant and then co-restrict to come down with a sign there. Here K is the center of B. So these are some properties which are well known. F3 is 0 for A is equivalent to saying A is a first construction. So you can find D and mu such that A is isomorphic to JD mu. And G3 is 0 is equivalent to saying A is reduced. That means A has 0 divisors. And this is a consequence of Merkurjev-Suslin theorem because, for example, here, to say this is 0 means this is 0, and that one knows if and only if mu is a norm from D. And when mu is a norm from D, in the first construction, we know it becomes split. So in the first construction case, you will get split. And in the second construction case, when mu is a norm from B, you get a reduced Albert algebra. It may not be split in that case. So G3 invariant detects whether the algebra is division algebra or not. F3 detects whether the algebra is first construction or not. Here I have goofed up. Automorphism group of A as an algebraic group is anisotropic over K if and only if it had been better if I had mentioned what is isotropic here. But let me say this anisotropic over K if and only if F5A is non-zero, or I should have written here, or G3 of A is non-zero. So one of those two invariants, F5 and G3, should not vanish. Then and only then the group is anisotropic. In other words, the group is isotropic over K if and only if G3 is 0 and F5A is 0. So those two invariants should vanish together to talk about isotropy. So by definition, isotropic means there is a K-split torus living inside the algebraic group. So this is a simple algebraic group. There I am defining isotropy by demanding there be a non-central K-split torus. As of now, this question is again open. One doesn't know if Albert algebras or groups of type F4 equivalently are determined by the invariants. Except the theorem of Springer, which said that reduced ones are determined by F3 and F5. And there is some little bit of progress due to Rost. No more general results are known in this direction. So this is completely open really. And I also need to speak a little bit more on mod 2 invariants. So let me go back to these degree 3 Jordan algebras of sigma symmetric elements living inside a degree 3 central simple algebra. So here again I have this, I just had the book in mind, but I think the result is this notion, and this result are due to Hale, Knus, Rost and Tignol, not Knus Mercury. I have goofed up here, I'm sorry about that. I had the book of involutions in my mind and that made me commit the mistake. The invariant F3 of B sigma is then defined as F3 of the Albert algebra JB11. And one knows that this invariant classifies the involution on B. So if B is fixed here, then if two involutions have the same F3 invariant, give you the same F3 invariant, then those involutions are equivalent. And one definition here we call sigma distinguished if the F3 invariant vanishes. And the theorem here is that you can always twist an involution to get a distinguished involution. So there exists a symmetric element V, sigma symmetric element, such that inner conjugation by V composed with sigma is distinguished. So there are always such involutions possible. And finally, I mention a formula for F3 in general. So if you have a second construction expression for A, anyway for first construction F3 is 0. So you may assume this is the second construction. Then the F3 is given by F3 of B sigma U. So this is the formula that we will use. Next, I'm running out of time. Let me quickly mention what are isotopes of Albert algebras again. Very special.
No. You have time. You have time. Do not worry for time.
Sorry?
You have time. You have time.
Okay.
Do not. There is no reason to worry.
Yeah. So are there questions so far? I apologize for not stopping and asking before, but if there are questions, I'll be happy to clarify. Yeah, so let me define in a shortcut manner what an isotope means. We say that Albert algebras A and A prime are isotopic if their norm forms are similar. That means there is a K-linear bijection F from A to A prime such that norm A prime of Fx is a scalar multiple of norm A of x, and this scalar is fixed here. For all x, this equation should hold. So then we define these algebras to be isotopic. And one knows that if A and A prime are isotopic, then F3 and G3 invariants of A and A prime coincide. And again, converse of this is not known. So one doesn't know that if F3 and G3 of two Albert algebras are same, then are they isotopic? This is again completely open. A very important problem and very deeply related to the classification of Albert algebras with in terms of invariants. So if one solves this, then one has classification up to isotopic. So it's a very related question. So let me describe what an isotope means now. So start with an Albert algebra A and take V in A. Then one can always embed V in a 9-dimensional subalgebra of this type. So that is fine. You can always do that. And then there is a theorem of, I believe, Tits, saying that then given such a subalgebra of A, you can always write A as an Albert algebra of second construction type. So you can find suitable parameters U and mu so that A is JB sigma U mu. And then given this V, assume V is invertible. I should have demanded here V to be invertible. Then I can take this as my up to isomorphism. The V isotope of A is the Albert algebra J B sigma V. So this is the twisted involution twist by the inner conjugation by V. U V hash. So this or sharp norm B of V, so reduced norm of V times mu. So this is a second construction Albert algebra. This we will call the V isotope of A. The definition of sharp is V times V sharp is the reduced norm of V. So this always makes sense. So one can show, I mean, any isotope of A. Remember, isotope means norm forms are similar. Up to isomorphism looks like this. So we will take this as granted now, this result, that if I know all these kind of, remember, V embeds in some such algebra, and then I have this expression, and then I am describing AV. If I embedded V in some other C tau plus, then I'll have a C tau V new kind of expression, and then I can write down with respect to that. So these are determined up to isomorphisms. So I will really need a little bit of this, nothing more. So I will come back to this if I need it. Don't worry. So there is a theorem of Petersson and Racine, which says that if A is an Albert algebra over K and L is a cubic field extension, so that's important. And I know that L reduces A. That means A tensor L is reduced. Then they prove that there is a V isotope of A that contains L as a subalgebra. So this is really a crucial result I need. And just as a token remark here, two reduced Albert algebras are isotopic if and only if their coordinate algebras are octonian algebras are isomorphic. This is, I believe, due to Albert and Jacobson. Given an Albert algebra A over K, one knows that the F5 invariant vanishes if and only if you can find a subalgebra in A where sigma is a distinguished involution. So this you can find in the book of involutions, this theorem proved there. Finally, I come to the solution of the promised result. So I hope to finish on time. Let's see. So the theorem says that if A is an Albert division algebra over K, then I can always find W in A such that the W isotope of A is cyclic. So first is we can write, as I said, we can assume A is a second construction, because when A is a first construction, we already know it is cyclic. So let's forget that case. So A is a second construction, write it like this. And we can normalize, there is a normalization process. I can assume norm U is 1 and norm of mu is also 1 from K and B respectively. I may not need this, but just maybe I need it, I don't remember now. Let's take V in B sigma plus such that sigma V is distinguished. This can always be achieved by the result I mentioned. You can always twist a given involution of second kind on a degree 3 algebra to get a distinguished involution. So let's choose V to be such so that sigma V is distinguished. And remember, distinguished means F3 invariant of this object is 0. Now construct an Albert algebra A prime as with respect to the parameters B, sigma V, 1 and mu. So I have fixed this expression for A, B, sigma, U and mu. I am cooking up this Albert algebra J, B, sigma V, 1 mu. So what do we observe here? F3 of A prime is by the formula for F3 I mentioned, F3 of A was F3 of B sigma twisted by U. So F3 of this Albert algebra therefore will be F3 of B sigma V, and sigma V being distinguished, this is 0. So F3 of A prime is 0. And what is G3 of A prime? G3 of A prime is the co-restriction up to sign of B cup mu. So that is exactly same as G3 of A also. When discussing G3 invariant, the involution and U don't come into picture. Only B and mu come into picture. So G3 of A and G3 of A prime are same, and F3 of A prime is 0. So this is what we observe. And since F3 of A prime is 0, we know that by the characterization of first Fritz constructions, A prime can be written as a first construction J, D, comma lambda for suitable D and lambda, right? And A prime, because G3 is A is a division algebra, G3A is non-zero, so G3A prime is non-zero. In particular, D is a division algebra, and therefore A prime is a cyclic algebra using Wedderburn theorem, if you like. So fix a cyclic cubic subfield here, call it L. Then obviously A prime tensor L is reduced because it contains L tensor L that has 0 divisors. So it will imply finally that A prime tensor L is reduced. Therefore, I forgot to mention G3 is compatible with base changes. So G3 of A prime tensor L, because G3 of so because A prime tensor L is 0, G3 of A prime tensor L is 0, which is also G3 of A tensor L. Because see, I have deduced here G3 of A and G3 of A prime are equal, and this is compatible with base changes. That means over any extension, I can commute the base change with G3. Maybe I should be careful there. No, that's fine. So this is therefore 0. What does that tell me? That tells me A tensor L is reduced. So here A prime tensor L is reduced because L is contained in A prime. So that implies A tensor L is reduced by this vanishing of G3. Therefore, applying Petersson and Racine's theorem, we get that a suitable W isotope of A contains L as a subalgebra. So this is the proof of cyclicity result modulo isotopy. So this is the end of my talk also, and there are some references here, not exhaustive list, very minimal in fact. This is the paper on exceptional Jordan division algebras of Albert, where this problem was raised. This is the paper, these are the papers. This is the paper of Petersson and Racine where they prove their cyclicity result. And this is the paper for cyclicity theorem that I mentioned. And these are the two papers where Nazareth was recently settled. Yeah, so the list is not exhaustive, but some references. So this is where I stop today. Thank you.
Ask a question concerning in the standard way. I think this is a very nice result, also very much in the spirit of Jordan theory, which says very often that results one wants to obtain only hold up to isotopy. So that's quite a general phenomenon. On the other hand, your result doesn't exactly answer the original question raised by Albert. My
Right.
question to you is, what is your guess? Is the answer to Albert's original question yes or no? What do you think?
Well, it's exactly what Philip mentioned about the general cyclicity problem. People are suspecting it may be false for central division algebras. And here, I believe, so I saw a result of Philip on E8. So I believe this is just a hunch, and I have some partial results on this. I have not. I have to push myself harder to get a condition on three torsion in the group of k rational points of F4. So start with an Albert division algebra and look at the automorphism group it gives. So that is a group G of type F4. And let's look at GK, the k rational points of G, and look at three torsion there. So I somehow believe that this conjecture can be reduced to looking for three torsion elements satisfying certain properties that similar to what Philip had for E8. And in fact, you mentioned for F4 also, right? In Philip?
You mean in my paper?
Yes.
No, yeah, yes. I was just saying that yes, if we take the picture, relating central simple algebra of degree 5 and
Right.
an element of order 5
Correct. Correct.
of a special kind in E8. So if we do it for 3 and F4, well, that provide an alternative proof of Vederburn theorem. Okay, but provided, of course, there is a cubic root of unity. And cubic roots are I mean, this is a strong assumption, as you have seen.
No, what notes? So I was suspecting that as you prove there that the order 5 element should normalize a k split torus, isn't it?
Yes, yes.
Yeah, so here I suspect the condition should be on certain rank 2 tori in F4. I'm just throwing out some ideas, but I have to write them down. I have not written them up yet. But certain rank 2 tori that order 3 element normalizes certain type of rank 2 tori. I think they should embed in A2 type k rational subgroups. So there is some kind of relation with such elements of this cyclicity problem, I believe. So Holger's question, I'm sorry, but I am not even able to solve a single element if I don't have a cyclic extension. So that led me to believe that we need these order 3 elements in the automorphism group.
Okay,
Maybe
very good.
you have a paper on that. Some student of yours, in fact, I remember worked on this at some stage. So
Yeah,
maybe there
right.
is something I don't know.
Okay, thank you very much.
Yeah, it will be amazing if you can prove this without the isotope condition. I believe it is true, but it doesn't mean anything.